Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 5 of module 7. So this is the last lecture of this module. In the last lecture today, we are going to cover the following concept. Before we will start the lecture, we will have a small recap of what we have learnt in the previous lecture. Then we will be learning about the spectral resonance peaks, and after that, we will be learning about physical dispersion due to anelasticity, and then we will see how the quality factor varies within crust to the inner core, and then we will have a summary of the entire module today. As far as the recap is concerned, we learned that for the damped harmonic oscillator, displacement can be given as displacement as a function of time t, that is equal to a naught e to the power iota omega t plus iota beta, that is further equal to a naught e to the power iota bt e to the power iota omega t, where a is basically equal to omega, that is equal to omega naught in bracket 1 minus 1 by 4q square to the power under root, and b is equal to omega naught upon 2q. So p that was given in the previous lecture was equal to a plus iota b. So the values of a and b are like this, and the relaxation time for the seismic wave to reduce its energy to 1 by e times of its initial value can be given by this particular expression. The time for 1 by e reduction, that is equal to 2q by omega naught, and the quality factor is inversely proportional to the damping factor gamma. So the smaller the damping, the greater the q will be. So for the higher value of the q, the damping will be smaller, and for a smaller value of the q's, the damping will be higher. And the energy decay can be given by this expression. We can write energy as a function of t, that is half small k a t square, that means amplitude as a function of time, and k is the spring constant, that is further equal to half ka naught square e to the power minus omega naught t by q, and this particular thing over here is the initial energy, that is E naught, and the final equation for the energy decay will be E naught E as a function of t, that is equal to E naught e to the power minus omega naught t by q. And the quality factors for the attenuation can be formulated as Q inverse. So Q inverse is basically considered because it is directly related to the reduction in amplitude. So Q inverse value will be lesser, then that means attenuation is lesser, and Q inverse is equal to 2c star by c, and the attenuation for the shear wave velocity in terms of quality factor inverse is mu star by mu, that is the shear modulus. Similarly, for the p wave velocity, k star plus 4 by 3 mu star by k plus 4 by 3 mu. And if you know the value of the amplitude at 2 consecutive cycles, then the quality factor can be deduced from those values of amplitude at 2 consecutive cycles by this particular expression, which says that Q is equal to pi by ln A1 by A2. And let's start with the lecture today. And in the previous lecture, we saw the formulation for the damped harmonic oscillator. Today we are going to have an external force or the external driving force that will be the frequency dependent on the harmonic oscillator. So it will be called as driven damped harmonic oscillator. So the formula for the driven damped harmonic oscillator will be something like this. This is the expression where it is something like this: d square ut by dt square plus gamma dut by dt plus omega naught square ut, that will be equal to the driving force, that is e to the power iota omega t. And the solution is found using the trial solution. That means the solution for this differential equation can be given something like that. That means u as a function of t is equal to a as a function of frequency e to the power iota phi omega. This is basically the phase term into e to the power iota omega naught t. And when we substitute this thing into equation 1, then we can yield the amplitude response, that is amplitude as a function of frequency, and also the phase response, that is phi omega. And the amplitude response will be equal to something like this, and the phase response will be something like this. So you can see that the amplitude response and the phase response both are depending upon the value of the gamma. That means amplitude and the phase responses depend on the damping factor gamma. And the resonance curve shows how the damped harmonic oscillator responds to the frequency dependent driving force. So basically, the closer the driving frequency omega is to the oscillator's natural frequency, the more the oscillator responds. So basically, when there is no attenuation, or in case of the undamped harmonic oscillator, the peak or the response of the amplitude will be basically infinite. So if you look at this particular diagram here and this one, both are basically the amplitude and the phase responses with respect to the frequency. So in this particular case, the oscillator is having the higher value of the quality factor for this one. And if you will normally see that the value at the value of the natural frequency, the peak appears for different value of the quality factors. And if the quality factor is highest, that means the attenuation is low, the amplitude will be larger. And in case the quality factor is low, the attenuation will be larger, the amplitude will be little smaller. And in case of the even lower value of the quality factor, the amplitude will be very smaller. So basically, the at the natural frequency, the amplitude's peak is appearing, and this is for the damped harmonic oscillator. If suppose there will be the q that is equal to infinity, and gamma is equal to 0, that means the damping factor is 0 and the quality factor is infinity, then you can expect that this peak should go to infinity. That means it will show an infinite response. If we look at the phase response curve here, that is with the variations of the frequency, then we can see that the value of the frequency is having the lowest value 0 and the highest value 2 omega naught. And at these values, the phase response will be varying from 0 to basically minus pi here. And at the value of the natural frequency, omega naught, the phase response will ideally be equal to this much. And there will be three commonly considered applications of resonance in seismology. First is the earthquakes excited the normal mode of the earth, and these modes form a set of the damped harmonic oscillators. So the amplitude spectrum of a long period seismogram contains peaks that corresponds to the net resonance curve for each mode multiplied. The width of a peak depends on the frequencies and amplitudes of the mode's singlets and the mode's damping. And another application is for the seismometer, and which can be viewed as the damped harmonic oscillator, whose natural frequency and the damping control their response to the ground motion. Another application is to design the earthquake resistant structures, because buildings are most vulnerable to ground motion with frequencies that is close to their natural frequencies. So damping is added in order to reduce the resulting motion. And an important consequence of seismic wave attenuation is physical dispersion, and physical dispersion is different from the geometrical dispersion. In the physical dispersion, the waves at different frequencies travels at different velocities, but in the geometrical spreading, it basically depends upon the thickness of the medium. So in physical dispersion, the intrinsic velocity of waves in the medium varies with frequency. And if you look at these diagram, in the ideal case where there is no dispersion, that means all frequencies are going to arrive at the same time. But in case if you introduce some dispersion, then the pulse will broaden out like this. That means the frequencies, different frequencies are arriving at different time. And let's suppose this is the time of arrival here. So you can see the different frequencies are even arriving. Some of the frequencies are even arriving at lesser time than the arrival time, and this condition is known as acausality, and we basically don't want it to happen. And in case if you look at the rightmost figure, the pulse is including with the physical dispersion, which makes the lower frequencies wave travel more slowly, so that the frequencies that were arriving earlier than the arrival time will now do not arrive before the highest frequency component. And we can see this mathematically, and for this purpose we will assume a delta function wave. That means a pulse of infinite height and unit area that will propagate through a homogeneous elastic medium with intrinsic velocity c. So this is the direct delta function, and there is a property to the direct delta function is that if we take integral of a function having the product with the direct delta function will produce the function at the value t naught. And the Fourier transform of the delta function, if we are going to do using this property, then you will get the Fourier transform for the integral having the value at x by c. That means it will be equal to e to the power minus iota omega x by c. That will show that the delta function is made up of wave of all frequencies. If there is no dispersion, all the frequencies travel at the same speed and will arrive at the same time. The effect of the attenuation as a function of distance and the frequency can be written something like this in terms of the amplitude as a function of frequency is equal to a naught e to the power minus omega x by 2c omega 2cq. And the complete solution we will find after taking the product of both of these functions, and or you can say both of these expressions. And the final solution will be given after you multiply equation 2 and 3, and then we will use the inverse Fourier transform to return to the time domain. So after you return to the time domain, after taking the product of both and taking the inverse Fourier transform, then you will get something like this. And then after you evaluate this particular integral, then the value of the displacement as a function of time and the distance can be written by this particular expression. And the what you will observe, the delta function is broadened by attenuation into a wavelet that is basically symmetric about the maximum value at t is equal to x by c. And there is a problem with this solution that some of the energy is arriving before the actual arrival of the seismic wave, and which we should not let it to happen. So that condition is known as non-causality, and we want to move towards the causality of our solution. That means we are going to consider that all the displacement that are arriving before the arrival time should be equal to 0. That means uxt is equal to 0 for all times that is having the values less than x by c, where c is the c infinity, that is for the phase velocity of the infinite frequency waves that arrive first. So one such dispersion relation for phase velocity as a function of frequency is called Asime's attenuation law, and that is given by the phase velocity as a function of frequency is given by this particular expression, that is depending upon c naught in bracket 1 plus 1 by pi q ln omega by omega naught. So this C naught is basically the reference velocity corresponding to the reference frequency omega naught, and this relation is basically provides the needed causality because the resulting pulse has high frequencies arriving at or soon after t by is equal to x by c infinity, whereas the low frequencies arrive later over a duration depending on the value of the quality factor. And if we take equation 4 into consideration, the p wave and s wave velocity vary as a function of time period, as beta as a function of time period will be equal to beta at time period is equal to 1 second in bracket 1 minus ln time period by pi q inverse mu, and alpha t will be equal to the initial value of the alpha, that is at time period 1 in bracket 1 minus ln t by pi in bracket ln q inverse plus 1 minus l qk inverse. Here l is equal to 4 by 3 beta by alpha to the square, and this particular phenomena causes a discrepancy between the seismic velocity structure found by inverting observations of long period normal modes and the short period body waves, and the velocities inferred from normal modes are consistently slower than those from the body waves, and this is what it should be. Body wave attenuation we can characterize by considering the physical dispersion due to the anelasticity, and it can be characterized using the parameter T star. So basically if a ray travels through a region of constant Q, the value of T star will be equal to T divided by quality factor, and because the Q varies within the earth, so we can derive T star by integrating along the entire ray path. So that means T star will be dt by q integral, and in the discrete mode it will be like sigma I is equal to 1 to n delta ti by qi, where delta ti and qi are the travel time and the q values on the ith path segment. So for p wave, the t alpha star is often about 1 second, whereas s wave it is about 4 seconds. The value of t star increase with increased distance, but are also affected by the number of passages through asthenosphere. We are going to see variations of Q in the crust to the inner core, and attenuation in the crust we can see up to a depth of 60 km on the x-axis, and you can see the Q inverse for the shear wave velocity is on the topmost x-axis and the bottom the inverse of it. So attenuation is inferred in all regions of earth except for liquid iron outer core, and varies greatly both laterally and vertically. And in the crust, if we talk about the greatest attenuation, that means lowest Q or highest Q inverse occur near the surface. So near the surface you can see higher amount of the attenuation happens, and that is presumably due to the presence of the fluids, and attenuation is basically lowest in the depth range of 20 to 25 kilometers, and then it basically increases with depth, and that may be presumably due to the increasing temperature with depth. And Q basically in the upper crust is roughly proportional to the time since the last major tectonic activity, and regional variations in Q are often studied using this LG wave, which is considered to be the superposition of higher mode surface waves that give prominent arrivals in continental region. If we consider the upper mantle attenuation variations, then the attenuation in the upper mantle, it also varies with depth, and lowest value of the quality factor can be found in the asthenosphere, which ranges in between 80 to like 220 kilometers depth. At these depth, the temperature basically approaches and perhaps basically exceeds the melting temperature of the rocks. So a small percentage of the partial melt will be existing over there at those depths. And this pattern of attenuation is similar to that for the seismic velocities, which are lowest in the asthenosphere. If we consider the Q value for the asthenosphere, which increases gradually with depth, and presumably because the temperature is increasing at a slower rate than the pressure, and Q value for the shear modulus increases with depth through lower mantle, reaching values in excess of around 500. And there is some indication that attenuation is enhanced in the D double prime region at the base of the mantle. And for the outer core and the inner core, uh, there is no attenuation for P wave for the outer core, and it will be significant attenuation for PKI capital IKP. That means the wave is traveling in the mantle as P and in the outer core as K, and as soon as it enters in the inner core, it becomes capital I, and then after it comes out in the outer core, it becomes K, and then in the mantle it becomes capital P again. So it is significant. The value of the attenuation is significant for the PKI KP wave that is traversing through inner core, that yields QK estimates in the range of 150 to 300, and where the temperature vary over short distances, a significant attenuation variations may occur. So this is the summary of today's lecture, or you can say the summary of the entire module. So with this lecture, we are going to finish module 7. So summary of today's lecture goes like this. Any material in which more than two elastic constants are needed are basically known as anisotropic material. Minerals and the rock comprises anisotropy either due to the lattice preferred orientation or the shape preferred orientation. They are also known as LPO and the SPO. Transverse isotropy is oftenly characterized by three parameters. Those are zeta, phi, and neta. And if the material is isotropic in nature, then the parameters are equal to 1. And if there is layered structures, then the value of zeta will be greater than 1 and phi will be less than 1. For the azimuthal anisotropy, the P wave velocities with azimuth will vary something like this using this expression, where P wave velocity is depending upon the value of the azimuth theta, that is equal to a1 plus a2 cos 2 theta plus a3 sin 2 theta plus a4 cos 4 theta plus a5 sin 4 theta. The value of the 4 theta will be insignificant in case of teleseismic studies. The magnitude of anisotropy can be characterized by this parameter k, which is equal to the maximum velocity minus minimum velocity divided by mean velocity, and this magnitude of anisotropic k is minimum for garnet and is maximum for the sheet silicates like mica. As shear wave travel across the mantle and the crust, they can split when traveling through anisotropic media that serve the basis of the shear wave splitting to study the lithospheric anisotropy. So in case, let's suppose this is the mantle, here you have outer core and this is your inner core, and a ray start off from a location of hypocenter as S wave. As soon as it encounters this outer core boundary, the component of this S wave, that are SH and SV wave, the SH wave will not go through the outer core because it is liquid, and SV wave will basically convert into the K wave, and it will travel through the outer core. As soon as it will encounter this boundary here, that is the outer core and the mantle boundary, then it will convert into the SV component. So it will go as SV wave into the in the mantle, and if there is anisotropy present in the upper mantle over here in this particular region, this SV wave will convert into its component of the quasi S1 slow and the fast wave, and that will be preferentially in the direction of olivine crystal. Those are prominent in this anisotropic region of the mantle. And after it enters, then the quasi S1 fast wave will be traveling faster than the quasi S2 wave, and as soon as it will comes out of the anisotropic material, then the delay we are going to study between both of the waves, and also we are going to see what kind of polarization angle it has. Using both of them, we can do that using the shear wave splitting measurements. We would normally not expect any SKS on the transverse component, but anisotropy yields a combination of both the fast and the slow polarizations on both radial and the transverse components that are given by RT is equal to ST cos square phi plus ST minus delta T sin square phi, and TT is equal to ST minus delta T, where delta T is the splitting time, or you can say the delay time between both of the S1 and S2 wave, multiplied to sine 2 phi. And source of anisotropy in the upper crust is the presence of the fluid filled cracks, horizontal sediment layers, included dikes, preferred orientation of olivine crystals yielded by spreading process. Seismic anisotropy within continent is thought to reflect crystal alignment created during a tectonic episode and then frozen in. For plate collisions, the fast axis is usually subperpendicular to the principal stress axis or parallel to the resulting orogenic belt. And as we have seen in our previous lecture, the anisotropy in the Pacific Ocean is derived by the parameter zeta, and this parameter is depending upon age and the depth. When it is greater than 1, that means the love wave velocity is faster than rally wave velocity, and it further indicates the horizontal mantle flow. In case zeta is less than 1, then love wave velocity is lesser than rally wave velocity, and it indicates the vertical mantle flow. The geometrical spreading, that is one of the way of attenuation, since we studied about the various processes through which the attenuation may occur, one of which is geometrical spreading, another is reflection and transmission, third one is the scattering, fourth one is multipathing, and the fifth one is the intrinsic attenuation or anelasticity. So basically, the seismic velocity depends nearly linearly upon temperature, whereas attenuation depends exponentially on the temperature. Thus, the combining velocity and the attenuation studies can provide valuable information about the structure of the Earth. Because the Earth is a sphere, the ring wraps around the globe, making the energy per unit wavefront of the surface wave vary as 1 by r is equal to 1 by a sine delta, if where delta is the angular distance from the source. If it is equal to 90 degree, then the amplitude will be minimum, and if it is maximum, that means 0 degree or 180 degree, the amplitude will be maximum. For body waves, because these travel in the form of spherical wavefront, the energy per unit area will be depending upon 1 by r square, and amplitude will be decreased as 1 by r. So you can see that the surface wave attenuation is smaller than the body wave. So seismic waves refract towards low velocity anomalies and away from high velocity anomalies. When multipathing occurs, the seismic waves arriving at a receiver can be viewed as having taken some ray path in addition to the direct path, and so have sampled a larger region of the Earth. When heterogeneity is large compared to the wavelength, we regard the wave as following a distinct ray path that is distorted by multipathing. Scattering is especially important in continental crust, which has many small layers and reflectors resulting from billions of years of continental evolution. The main arrival has a polarity related to the direction of propagation, but the scattered energy arrives from various directions, shows little or no preferred particle motion. For the damped harmonic oscillator, the displacement can be given as ut is equal to a naught e to the power iota omega t plus iota bt. That can further be written as like this, and when we solve it for the values of real part of p and the imaginary part of p, that is a and b respectively, then a is equal to omega naught 1 minus 1 by 4 q square to the power 1 by 2, and b is equal to omega naught by 2 q. Relaxation time, that is the time for the energy to decay to its 1 by e of the initial value. That means that is T 1 by E is equal to 2Q by omega naught, where Q is the quality factor. Q is inversely proportional to the damping factor gamma. So the smaller the damping, the greater Q is. The energy decay is given as Et is equal to 1 by K AT square, where AT is the amplitude with respect to time and K is the spring constant. When we further expand it, then it will become half K A naught square e to the power minus omega naught t by Q, and that can be written as E naught e to the power minus omega t by Q. That means energy decays faster than the amplitude, or you can say twice as faster than the amplitude. So quality factor can be formulated as Q inverse is equal to 2B by A is equal to 2 omega star by omega. Q inverse is equal to 2C star by C. So quality factor for the P wave and the S waves can be written something like that. For the S wave it is mu star by mu, and for P wave that is K star plus 4 by 3 mu star by K plus 4 by 3 mu. And in case for the damped driven harmonic oscillator, or you can say the solution of the forced driven oscillator is something like this. Displacement with respect to time is equal to a omega e to the power iota phi omega e to the power iota omega naught t. So phi omega is the phase response and a omega is the amplitude response of the driven damped harmonic oscillator. So that those values for the amplitude response and the phase response are like this and like this. Both are depending upon the damping factor gamma. In case of the physical dispersion, the intrinsic velocity of the waves in the medium varies with frequency, and P and S wave velocities alpha and beta vary as a function of time period as given by these expressions. So body wave attenuation is often characterized using the parameter T star, and T star is integral dt by Q. Q is the quality factor that is further can be written in the discrete form from I is equal to 1 to n, that is delta T Ti by Qi. That is the values of the time and the quality factor in the ith segment of the ray path. So these are the references of the module 7, and we are going to meet for the module 8, and we are going to start with lecture 1 of module 8, and thank you so much. Bye bye.